All right, good morning, everybody. Make sure that I can be heard and slides are being seen. Give me a, thank you very much. Perfect. Okay. So just some announcements. The problem set that hopefully you are all working on is due Friday at 10 o'clock. So hopefully I've not used that the Canvas upload assignment feature. Has anybody uploaded it yet? Okay. Or have you, I assume it's been Octane used that the feature before, so I'll have to figure out where I even go to look for the assignments once they're uploaded, but I will try to figure that out. But hopefully you know how to do that. And then quiz 8 will be available on Friday at 11 and will be available until Saturday morning at 11. So Friday at 11 a.m. to Saturday 11 a.m. So you have 24 hours to complete quiz 8, same format as before. Okay, so hopefully that will all work out fine, and I'll try to adjust it so that you can, I'm not sure I'm going to make the answers available, but at least you'll see your score. I'll try to figure that part out so you don't have to wait until Saturday to see the scores. Okay, any questions on any of those two things? Okay. Okay, and we will get to if you haven't done the problem set yet, we'll get all those, hopefully all your questions addressed today. Okay, so quick review. We talked about the difference between pasteurization and sterilization. And we talked about the difference between clinical sterility and commercial sterility. So when you go to the dentist, you may know what movie that's from. Great movie. Okay, but in any event, you'll have to figure that one out. Clinical sterility is the absence of all vegetative microbes and their spores to non-detectable levels. What's left? Nothing, theoretically nothing. Here's another iconic figure. This is the famous Andy Warhol Campbell Soup artwork. But in any event, aside from that, in commercial sterility, we have the absence of all vegetative microbes and pathogenic spores to non-detectable levels. What's left? Thermal tolerant, very, very thermotolerant spores that can only germinate and grow at high temperature. So under normal conditions, they are not a problem. So canned foods on the shelf may have a few spores, but they're not pathogenic and they're not going to germinate. Note that in both of these, vegetative cells are killed. no vegetative cells. All right. And then we talked about determining time and temperature conditions, um, um, and how we approach those questions. Okay, we do survival curves, and we talked about D values that we get from the survival curves, survivors in some units versus time in some units, and the time that it takes to go from one to decrease by 1 log, 10 to the 3 to 10 to the 2, or somewhere anywhere along that line, is determined as the D value. Okay, and then we posed this question the other day, um, where I gave you 3 unknowns and you had to match them up, and you correctly guessed that the flatter the line, the longer the D value, the greater the D value, the longer it times to reduce the population by a log. And you correctly surmised that the name Thermophilus means this organism has some sort of thermal tolerance, whereas the psychotroph has the least. So that's how you guess that. There's a general rule of thumb. I like kind of general rules of thumb. They help you remember things, that the better equipped a microbe is to grow at low temperature, like Pseudomonas, the more sensitive it is to high temperature. And the more tolerant, or the more thermophilic or thermogenic a microorganism is, the more tolerant it is to high temperature. Okay, so psychotroph sensitive, the thermophile more tolerant. Okay, you can see those D values: 5.4, 2.7 for the Listeria, 0.6. The lower the D value, the more sensitive. Okay, now I said before, when you're trying to determine thermal kinetic parameters, you can't look them up. Well, you sort of can go to the literature. And so this is from an older textbook, and it has D values for all these microbes, vegetative microbes and spore microbes. So you can kind of look them up, but this only gives you a general idea. They ultimately depend on the food and the conditions. So it says salmonella D value at 65, and even gives a range, a 10-fold range. So why such a big range? Well, it depends on, so in this table, they collected this from other experiments in the literature. So it depends. If the pH is low, then the D value will be short. Okay, if there's no antimicrobials in there, the D value could be large. So you can see there's big ranges, sometimes 10-fold ranges from the literature. So you can get an idea by going to the literature, but you cannot predict from the literature. Now, you can also learn, you can also see here that the D at 65 for this salmonella is in the order of about a minute. The D at 121, much higher, twice as hot, for spores can be 4 to 5 minutes. And so that's because spores are very resistant to heat. It takes a lot of heat to kill spores. Okay, and you can tell from this name, Thermophilus. It's got that same name, heat loving, that's going to be very resistant to temperature. Okay, so you can go to the literature and get an idea, but ultimately you have to do this empirically. You have to do experiments. Okay, so we talked about survival curves, and so you now know how to do those survival curves, because you have to do that for your problem set. Knowing a single D value, i.e., at a given D value at a given temperature, is nice, but what if we want to consider another temperature? So let me go all the way back here. So here are these D values at whatever temperature this was, 60 degrees. So for Strep Thermophilus or for Listeria, you can get this one D value. So this is a survival curve at 60 degrees for Listeria under those conditions, but that's only one D value. So the question is, what if I want to know the D, now it's 60, but 64 or 68 or 72? Can we make survival curves at every possible temperature? So here is that Listeria problem. So here's Listeria, survival curve at 54, 58, 62, and we can certainly get those D values at all those different temperatures. Okay. And let's say you are working in a product development lab as the resident microbiology expert, and you're developing a, I don't know, let's call it some sort of beverage product, and it has a particular pH, but you need, your boss says we need to our pasteurizer is set at a particular temperature, and that's what we want to process at. And so you did all these experiments, 54, 58, you did, these are laborious experiments. I showed you how you have to set these up and multiple samples, and then your boss says, we want to do this at 64 degrees or 65 degrees, and you didn't do that experiment. You go, oh, we're gonna go back and do another experiment, or do you? Okay, so can we make survival curves at every temperature? No. Instead, what you do is you plot D value, all those D values versus temperature. And the result is what we call a thermal death time curve, which is a great name for a rock and roll band. All right, okay. So here's what you do. So you go back to this, all these survival curves that you've made, and you collect the D values at those temperatures. And so now you have the D at 54, 22 seconds, D at 58, 11, and so forth. And this is what you're going to do for your problem set. You're going to get those D values at different temperatures. And then you make a thermal death time curve, plotting on the, again, this is on semi-log paper. And this time what we're going to do, we're going to plot D values on the y-axis and temperature on the x-axis. Okay, and then you're going to put your units in there. So again, D values were in seconds, and they range from 0.5 up to 22. So we have to make sure that we make our scale to accommodate 0.5 up to 22. So let's read off. 0.1 is here. What's this value? 0.2, 0.3, 0.4, 0.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, 20, 30, 40. So we can accommodate 22 and 0.5 and all the points in between. And then we simply put all of our temperatures that we had done, we had done survival curves. And now we just plot the points. 22, D at 58 was 11, D at 62 was 6. We plot all those points, and lo and behold, we get a thermal death time curve that's a straight line on semi-log paper. It's a straight line. Now what we can do is we can figure out what, if your boss said he wants to process, he or she wants to process at 64, you go to 64 and then you read across and you see that the D at 64 is 4 seconds. And so you never did the survival curve at 64, but you have a straight line here. And so now you can, 1, 2, 3, 4, now you can reliably determine that the D at 64 is 4 seconds. Okay, hopefully everybody sees that. If not, you're gonna have to go back and listen to either look at the slides or listen to the video, because you need to understand how you use this thermal death time curve, what it can tell you. It can tell you the D at any temperature along the scale that you've done this at. Okay. So what do we learn from a thermal death time curve? The D value at any given temperature. We also learn, and I apologize, but I didn't invent these thermokinetic terms, but they have another one called the Z value. The Z value is the inverse slope of the thermal death time curve, and it's the degrees necessary to decrease or increase the D value by 1 log. So if we go back to that line, now we're looking at the number of degrees necessary to increase or decrease the D value by 1 log. So if the D at 59 looks to be 10 seconds, and we go down to a log, 1 log less than 10 seconds, which would be 1 log, which would be 1 second, from 10 to 1. It takes 12.2 degrees, 12.2 degrees hotter. We have to raise the temperature 12.2 degrees to reduce the D by 1 log. So that makes sense. If we raise the temperature, we're going to get more killing. And if we raise it 12.2 degrees, we're going to increase the killing rate tenfold. Okay, does that make sense? So the Z value is always given when these D values are reported. Okay, so let's look at this. Here's a little problem. In theory, knowing a D value and a Z value, one can construct the thermal death time curve without even making a curve. You could use simple math to predict a D at any other temperature on the curve. For example, if the D at 74 is 24 seconds and the Z value is 6 degrees, what is the D at 80? Oh my gosh. Somebody want to do the simple math? It says simple math. 12, I see. Somebody else? $2.4. That's interesting. Somebody else? Somebody break the tie. I've got 1 vote for 12, 1 vote for 2.4. And I've got a whole bunch of undecideds. Okay, so let's look at it. Again, if we go back, I used this value 10 and 1, but it could have been 20. It could have been 22. I could have been up here somewhere, and the line would have still been the same. So don't get hung up because I didn't use I didn't use 10. I used 24. But a log reduction of 24 is, as Rachel said, 2.4. Okay, so if I went up 6 degrees, that's my Z value, I reduce the D by 1 log, so 24 to 2.4. So Rachel was right, okay? Okay, let's make even a harder question, semi-hard. After 48 seconds at 65, the population of Staph aureus in beef broth is reduced by 6 logs with a Z of 5. What is the D at 70? The D at 70. Okay, take a minute on this one. The answer is not E. I am 100% serious. Now I see that there's only handful of you here today. 1, 2, 3. There's only 5 of you online today. Oh my gosh, it's terrible. So I want to see 5 answers. I want everybody give me an answer. All right, come on, chime in. Make a guess if you have to. At least I have a guess. So I told Emily, I told you, it wasn't, I am serious. It's a hard question. All right. Okay, so first question is, even if I wasn't asking the D at 70, what's the D at 65? I gave you enough information to know that the D at 65 is you don't have to, okay, there's a chat. 8 seconds. How'd you know that? Because I said there was 6 log reduction at it took 48 seconds to achieve a 6 log reduction. So 48 divided by 6 is 8 seconds, is a 1 log reduction. So every 8 seconds, there's you get a log reduction. Then I said, I gave you the Z is 5 degrees. So if we went up 5 degrees to 70, you reduce that D value by 1 log. So from 8 to 0.8. So that is the answer, 0.8. Okay. So the D at 65 is 8, and the D at 70 would have been 0.8. Okay. Great question. Okay. The other thing that we can learn from the thermal death time curve is how heat resistant changes depending on temperature. So here is an example of 3 Clostridia, and the D value at, I don't know what this is, 111 or 110 or something like that, is the exact same, but the thermal death time curves are all a little bit different. Okay, so the heat resistance changes over this temperature range, even though they all have the same D at a particular temperature. So it doesn't happen often, but this can be the situation where that's why you need to know more than just the D value. You do need to know the Z value, which comes from the thermal death time curve. Okay. All right. Okay, so now we're starting to get to be able to answer the question. We now know how to measure death rates, but we still have to answer the question, what's an adequate thermal process? Or in thermokinetic terms, how many log reductions are necessary to achieve the desired level of destruction? Okay, in other words, is it 2 log, 4 log, 5 log, 10 log? What do we want to get? Okay, and again, we go back to some assumptions that we make based on what we know about microbial ecology. Okay, and it also depends on the risks that we want to assume. Okay, so the goal is safety, so we're always conservative on our risk. We want to minimize risk. In other words, you could arbitrarily say, well, I think a 2 log reduction is satisfactory. But again, if your knowledge of microbial ecology says, no, that's too risky, we need a 5 log reduction, then you have to be more conservative. Okay. So for example, canned foods require a 12 log reduction in Clostridium botulinum spores. So this is the dogma in the food, especially in the canned food industry. It's known as the 12D concept. Sometimes you'll see this as the minimum botulinum cook, 12 log reduction. In roast beef, that cooked roast beef example that I gave you before, like you see it at delis, require a 7 log reduction of salmonella. Okay, and then in fruit juice, the FDA requires a 5 log reduction of E. coli. Now, again, there's not too many requirements for other foods. So again, if you're pasteurizing beer or some other food, that's up to your own internal requirements. Okay, so now I'm going to introduce another term, and that's called the F value. And I think this is the last of these kinds of DZ and F values. The F value describes the total process time at a given temperature to achieve the necessary or the desired level of destruction. So for CBOT, I said it's a 12D process, means 12 times D equals F, the total time. Okay, and you could calculate that mathematically. Um, and so here for an example, if the D at 121 degrees, so that's kind of your normal canning temperature and pressure. If the D was a 7.0, so let's say it's a can of green beans, probably close to pH 7, is if the D is 0.21 minutes, then the F is 0.21 times 12 equals 2.52 minutes. That's how long at 121 would be necessary to give you a 12D process. Okay. And we use that Z equals 10 is kind of the reference value. But if the conditions were a little bit different, like the pH was lower or we were at a different temperature even, you can get the equivalent of this. You can, and we call that the F sub 0. You can get the equivalent of that at different temperatures. So at 121, you can get, if the pH was 5, that 12D value would only be about a minute. So you can get the same effect, but it might take a different amount of time. In contrast, if you were average, you can get to 12D. It's the same equivalency, might take longer. And if you put the pH low, put nitrite in there, so maybe that's canned, I don't know, canned ham, then you get the equivalent even quicker. So not 2.52 minutes, but 0.8 minutes. A third, it takes a third as much time. Here's the big question. Are these values reasonable? In other words, 12D for a can of green beans, will a can of green beans ever contain 10 to the 12th spores? What is 10 to the 12th? 10 to the 6th is a million, 10 to the 9th is a billion, 10 to the 12th is a trillion. Is it possible that your green beans could become 10 to the 12th spores? Seriously, I mean, that'd be hardly any room left in the can for the green beans. Okay, but let's just say, okay, that's what it says. It says we have to do a 12D process. The FDA says that. So let's say I didn't start at 10 to 12. I started at 10 to the 11th. That's how many. So this would be a survival curve for CBOT spores that you did experimentally. 10 to the 11th. The D, I said, is 0.21 minutes. So that's right here, 0.21 minutes. And at the end of 12D, 2.52 minutes right down here, you would have 10 to the minus 1 spores per mil. But we already said 10 to the minus 1 is the equivalent of 1/10 of a cell per mil, but it's also the equivalent of 1 cell per 10 mils, right? Or even 10 cells per 100 mils. So would you eat this can? Would you eat this can of green beans? Remember I talked about risk. What risk are you willing to take? You have a 12D process, but in theory, if this is a 100 mil can, you could have 10 spores. So would you eat that? How do you feel about your odds? Don't forget, CBOT germinates and grows, you're dead if you eat that without heating it. So, will a can of green beans ever contain 10 to the 12 spores? Not hardly. Washed and sorted green beans might contain a spore or two. So not 10 to the 11th. That's why I'm saying microbial ecology comes in here, because it's impossible to see that many. In fact, it's hard to do this experiment because I don't know any laboratory. If you tried to do this experiment in a laboratory, you would never get permission to have this many spores floating, in your laboratory bench. This is a Clostridium botulinum is a terrorism agent, in addition to being a foodborne pathogen. And so you would never be allowed to even do this experiment with 10 to the 11th spores in your laboratory, or it'd be unlikely. You'd have to be at one of those high security laboratories. Okay, so, but it doesn't really matter because you'll never see that many spores in a can of green beans. So let's just say an average can, 400 ml can, that's a good size can, has only one spore. That's a more reasonable expectation. So a 12 log reduction would mean that the average can would come out of the retort containing 10 to the minus 12 spores per can. So 1/1,000,000th of a spore, okay? So here's a more realistic situation where we start with one spore, and after 2.52 minutes, we have 10 to the minus 12 spores. Okay, so that's where I say risk. So now your chances are pretty remote that any one can will have a viable spore. Okay. So in other words, it's the same as saying there's a 1,000,000,000 to 1 chance that a spore will be found in a single can. Okay. Or if we processed 1,000,000,000 cans and you were really hungry and you ate 1,000,000,000 cans, you might get unlucky enough to find a CBOT spore in one of those cans. And I'm being facetious, but let's say you processed 1,000,000,000 cans. Okay, one of those could conceivably contain a CBOT spore. So if we did all those Campbell soup cans, one of those, in theory, could contain a CBOT spore. Okay, everybody follow that? That's why I introduced this concept of risk. Okay, because we can never get to 0. So, but we reduced the odds to 1 in 1,000,000,000. Okay, so hopefully you have now a pretty good understanding of this thermal process and this 12D idea. Now, the canned food industry is remarkably safe. Canned foods are remarkably safe. The only time you hear about a canned food causing a problem, like a CBOT problem, is usually at home when a homemaker cans food and doesn't have the right gauges and temperatures and pressures and so forth, and screws up. But the canned food industry does really, really well, unless there's a humongous process failure where somebody, usually human error, caused a problem, or as we'll see later, if the integrity of the can is compromised. Okay. And in reality, thermal process is even more conservative than the 1 in 1,000,000,000. For example, we round up so that 2.52 usually becomes 3 minutes. That's the F value. And we validate using resistant organisms. So I mentioned before that you would never want to bring CBOT spores. You certainly want to bring 1,000,000,000 CBOT spores into your laboratory. In fact, at a food company, you would contract that out because you don't even want those spores on site. But in reality, we don't even use CBOT spores. We use a surrogate, a strain. In this case, we use Clostridium sporogenes, and there's even a strain that we use of Clostridium sporogenes called PA3679. We use that one instead because it's not a pathogen, but it has a D value greater than 0.21 minutes. And so that makes a great surrogate because it's even more heat resistant than CBOT, yet we still expect a 12 log reduction. Okay. Here's a paper that came out some years ago. And remember, I talked about Chronobacter sakazaki. It's the organism that's in powdered milk that then ends up in infant formula. So here was a study, and they used 2 strains in their process laboratory. They were doing survival curves, and you can see the 2 survival curves at doesn't say what temperature this is. Oh, 58 right here at the title, 58. Two strains, 607 and strain 51329. Which is the better strain to base their thermal process on? 51329 or 607? Which is the better strain for them to develop their thermal process? Somebody give me an answer. So I got two different answers. Which one's more thermal tolerant? 607 is. This is the one you would use. This is for some reason, this strain's too sensitive. You want to use the one that's more thermal resistant, which is 607, right? The D value, you'd see, D value is, the survival curve they plotted on a log. They didn't use log paper. They just took the log of the number. So from 8 to 7, it's about 1,000 seconds. And for this one, gosh, it's really hard. It's like a few seconds. Okay. Okay. So you use a surrogate. The other reason why thermal processes are even more conservative is sometimes in some foods, CBOT's not even the target. The target is a thermophilic spore former that has D values not 0.21 minutes, but even greater than a minute might be the target. So for example, Bacillus stereothermophilus has a D of 3 minutes, 10 times higher than CBOT, and they'll use this one as the target for whatever reason, okay? And so if they got even a 4 or 5 D reduction for Bacillus stereothermophilus, that would be equivalent to a 24 or 36 log reduction for CBOT. Okay. And similar approaches might be used for non-canned foods as well. Okay. And then we're going to come to this in a couple of minutes. Come up and come down is also important. We'll get to that in a few minutes. Okay, so you understand now why canned foods are so safe. The process itself reduces the population by at least 12 logs, but probably more because we use more heat-resistant surrogates, or we even have targets where we round up, we use heat-resistant surrogates, and maybe our target is even more resistant than even the surrogate. Okay. All right. Okay, so some other factors to consider that also affect thermal processing. So for example, if you think of a can, the consistency of the food. Like for example, is it peas in a brine? Is it chili? Is it tuna? So all these things, the size of the pieces, the viscosity, the layering, it could be, will a chicken broth have a different consistency than cream of mushroom soup? Okay, viscosity can be important. Okay, container composition, glass, can. Other, container size and shape, big can, small can, shape of the can, whether the can is agitated during processing. Okay, now what do all of those things, all these things here, collectively ultimately affect? Do they affect D values? No. Do they affect F values? No, if they don't affect D values, they don't really affect F values, not directly at least. Rather, they affect heat penetration and heat transfer. So many of you are taking right now, I forget what it's called, Food Science and Technology 363 or whatever it is, the heat transfer course, right? I forget what that's called. But Food Engineering 1, you're taking a course on heat transfer. And that's what is so important here. So there are 3 types of heat transfer that occurs in foods. There's conduction, molecule to molecule, convection, movement via currents, And as in common, especially in canned foods, both occur, really common. So conduction occurs. So conduction would be, in a can, it would be like canned tuna or canned chicken, okay, where it's molecule to molecule and you heating the food from the outside to the inside. Convection gives you currents, okay? And here's a good example that will happen in a few weeks. Your turkey cooks by conduction, okay? But when you cook something in a pot, soup in a pot, and you see the boiling occurring, you know you're getting convection cooking, okay? And so here's some good examples. Again, fluid is going to be convection, and then get all the way over to here with solids, and form something viscous but not quite solid like pumpkin. Okay. Um, and then they talked about agitation. So in most commercial retorts for canning, they are, I'll show you a picture, but the cans are put in a kind of a cylindric retort and they're agitated, they're rotated. And so you're getting some heat, improved heat transfer as the cans are rotated. Okay, and so here is like a commercial retort. These long cylindric objects, here's the doors open and cans are placed in here, and then this thing spins. So you're getting good agitation. Okay. So let's now we have to now backtrack, and we talked about all the thermokinetic properties, and now I have to tell you have to rethink some assumptions. Okay, so you put a food in a however you're going to heat it. It could be in this retort. So you put the doors open. We put the food in here. So we put the food in a can. We seal the can and we put it in the retort. Okay, and now we're going to process it. But is that heating? If our temperature is if our goal is 121, is it get to 121 instantaneously? No, we've got to come up to 121. Okay, and we've also said heating is applied uniformly. And even if that can is agitated, it's not applied uniformly because there's heat penetration. So neither are absolutely true. I guess absolutely true is a redundant or oxymoron or something. Okay, so we have to account, or we can account for the come up and come down via integrating heating models. And this requires calculus, and good for you. I haven't had calculus in 45 years, so we're not going to go through the calculus, but in heat and mass transfer, that's the name of the class I was thinking of. They probably do this. Hopefully they do they show you how this is done. Okay. And we can account for this non-uniform heating by determining where the cold spot is in that food. So let's now look at two types of foods. We're going to go into a retort in a canned food, and that canned food, if it's like tuna, has a cold spot right here in the center. In conduction heating, the cold spot's always in the geometric center. In convection heating, it's not quite in there. The cold spot's right about here. Depends on the shape. But in convection heating, the cold spot's different. But in either case, we could stick a thermocouple into that can, and we could determine the cold spot. Okay. And I point that out because the D value and the F value is based on the time at the time that the cold spot reaches the target temperature. Okay. So the exterior might reach that target temperature very quickly, but the clock starts, if you will, when the cold spot reaches that temperature. Okay, so we put some canned foods in a retort, and we're measuring the internal temperature, the cold spot temperature. Okay, and this is time in the retort up to 6 minutes. Okay, so this is our starting temperature. We might be ambient. Okay, and here's our target temperature. So we're measuring, we have a thermocouple in that can at the cold spot. We're measuring it, and this is what that curve will look like. So it starts off, it's warm, it's getting hotter and hotter and hotter. So it's starting to heat 40, 50, 60. And right here, when it reaches 121, our D value clock starts, or our F value, if you will, starts. Okay. So the clock starts where the temperature at the cold spot is reached. And then we go 170 seconds, right? That's like the 2.52 minutes, if you will, for a 12 log reduction. So we get all the way here. And now it's been at the target temperature for the right amount of time. And then right here, we program the retort so it stops heating. And in fact, we want to cool this as quickly as we can. We don't want to overcook it, right? We said we don't want to overcook it. So the cans might come out and go into some cold water or do something. So we try to get it. So it only took 20 seconds to cool off. It took a whole long time, a couple of minutes to get it hot. Okay, everybody see that's how it works. Okay, so that's our F value, 170 seconds. Okay, now in reality, this is how they process cans. Huh? Hutkins, you just told us it takes 170 seconds. Whatever, was that 100? Yeah, it took 170 seconds. Now you're saying we're out of here in a few minutes. Well, this is the reality, because it's only at 121 for 20 seconds. So is everything I just told you wrong? Okay, no, I would never steer you wrong. Okay, so once you get to, let's say we're around, looks like around 70 degrees. It's 70 degrees. Those spores, if it's CBOT spores, they're pretty resistant to 70 degrees, but we might start killing them. But the D value at 70 is probably pretty large. So there's not much killing there. But there is a little bit of killing. And then we get to 75 degrees, a little bit more killing. And we get to 85 degrees, a little bit more killing. We get to 90 degrees. And so from here, once we get to 100 or so, there's some serious killing. Okay, the D value might be large, and it's only passing through 100 degrees for a few seconds, but there is some killing. Okay, and then the same thing on the reverse side. So now it's coming down, and it's coming down pretty quick, but there's killing every step of the way. Okay, and so if you knew calculus, you would be able to figure this F value over here, which integrates all of the killing that happens at the entire time. Okay, so there's killing here, especially right before you get to 121, at 118, 119, 117, there's real serious killing. Okay, so if you integrate that, then you'll realize it only takes 20 seconds at 121 when you combine it with all the killing that occurs, especially in this zone up here. You know, once you're above 100, you get even more killing. Okay, so that's a really important point. The come up and the come down also contribute to killing. Okay, hopefully that's a really important concept. Okay, and you're clear on that. Okay, and if I was and on the exam, I'm going to ask you to derive this calculation. No, I'm kidding. I'm kidding. All right. Okay, some other considerations as we wrap up. We have to be aware that some microbes have resistance to high temperature, there's stress response, there's sublethal effects, and we will not get to those today. We'll talk more about those later. And then there's some other factors, it's what organisms are in the food. We talked about spores being most resistant. There's physiological changes that can occur. Stationary phase, more heat resistant than log phase. So should you use stationary phase versus or log phase when you do a thermal death time study? You use stationary phase. Use the most heat resistant form of those cells. We'll talk more about stress adaptation later. Again, these are relevant when you do the experiments. More relevant on a practical basis is the composition of the food. So if the food contains sulfites or nitrites, you have to account for that. They usually reduce the D values. Sometimes they can increase heat resistance. And of course, we talked about pH. And that's how, and pH is indeed one of the major ways we can reduce D values and F values, lower the pH, lower the resistance. Okay. So for CBOT, for example, at pH 7, the D at 115, I don't know where I got this data, but they use 115 instead of 121. D value is 0.53. But as you get into the acid range, you can reduce the D value considerably, 4 times. And you get, and at 100 degrees, you could reduce it so that the D value is achieved simply, or at an acidic pH below 4.6, even 100 degrees will give you a 12D reduction. Okay, so before we leave the thermal kinetics, we've mainly been talking about high temperature canning temperatures, but probably more, I won't say more common, just as common as commercial sterilization are pasteurization. So again, we talked about ways we use heat, commercial sterilization and pasteurization. And there the goal was to kill pathogens, spoilage organisms, and activate enzymes, but we're not killing all the pathogens, only those capable of growth in that food. And we use pasteurization when more severe heat treatments aren't feasible, but the conditions are exactly the same, or the principles are exactly the same as for sterilization, except the target is not CBOT. The target depends on what the food is, okay? And again, our knowledge of microbial ecology. So we'll stop there. You have all the information necessary to get your problem set done. If you have questions, let me know by email, but don't wait till the last minute. So I'll answer questions up to Thursday night, but hopefully you won't have any questions, and some questions I will not answer if I think you should be able to figure it out on your own. Okay, so you should be able to make all the, I will emphasize for those of you that are listening, I think it says based on your knowledge of 8th grade geometry, you should be able to make all those curves. So that was a little bit of a clue there. Okay, so we'll stop there and see you on Friday.